In this video, we are going to review exponent rules. So first, we're going to start with an expression that has a negative exponent. And when we first talked about negative exponents, we looked at things like k to the first power over k to the third power. And we looked at this in two different ways. We first looked at this as k over k times k times k. And we realized that could be written as 1 over k squared, because we were able to look at k over k, which simplifies to 1. And those, we said it cancels out. We get 1 over k squared. And then we also looked at it as the pattern that when you're dividing expressions with exponents, you can subtract the exponents. So this was k to the negative 2 power. And so we saw that a negative exponent was the same thing as a positive exponent in the denominator. So this k to the negative 6th could be written as 1 over k to the positive 6. Okay, simplify p over 2 cubed. When we raise something to the third power, that means we're going to write that same expression 3 times. So we have p over 2 times p over 2 times p over 2. So if you look, we have 3 p's on top, so that's p cubed. And on bottom we have 3 2's, so that's 2 cubed. And if you wanted to, you could evaluate the 2 cubed and call that 8. You could also leave it as p cubed over 2 cubed. The next one, we have something raised to the 0 power. And we had learned earlier that anything to the 0 power is 1. So this just evaluates to 1. It doesn't even matter what's inside, assuming that none of these variables are equal to 0. Dividing expressions with exponents. You could imagine having 10 a's on top on the numerator and 5 a's on bottom in the denominator. And as we look for things that cancel out, that divide to 1, we would cancel out 5 of the a's on bottom with 5 of the a's on top, and we'd be left with 5 a's, a to the 5th power. And so our rule was we would subtract the exponents when we're dividing. 10 minus 5 is 5. Here's another expression that is cubed, so I'm going to write that expression 3 times. So I have s to the 4th power inside the parentheses, and I'm writing it 3 times because it's been cubed. So now if I were to count all of my s's, I have 4, 4, and 4, so that's 12 s's. So this is s to the 12th power. Okay, I have something raised to the 4th power this time, so I'm going to write it 4 times. So I have c to the 6th d inside each parentheses, c to the 6th. Because it's raised to the 4th power, I have 4 of them. So now if I look at how many c's I have 6, 12, 18, 24 c's overall. So c to the 24th power. And I have 1, 2, 3, 4 d's. So d to the 4th power. And there's an implied times in between there. And finally, and these weren't necessarily in any order of difficulty, x squared times x to the 8th. The way we visualize that was x squared is x times x, and x to the 8th is 8 x's, 1, 2, 3, 4, 5, 6, 7, 8, all multiplied together. And when I multiply those, I see that I just have a big long string of 10 x's. So this is x to the 10th. So as a quick review of what we just did, when I'm multiplying expressions that have the same base, these are both x raised to a power, I add the exponents. 2 plus 8 is 10. When I'm raising stuff to a certain power, really what we ended up doing was we multiplied the exponents. 6 times 4 is 24, and this is d to the 1st power. 1 times 4 is 4. So the rule would be when you're raising a power to a power, you multiply them. Same thing here, a power to a power, 4 times 3 is 12. When we are dividing things with the same base, these are both a raised to a power, we end up subtracting the powers. We subtract the exponents. 10 minus 5 is 5. We saw that anything to the 0 power is 1. We can do the same thing here. This is stuff to a power, so this is p to the 1st power, and 1 times 3 is 3. That's why we got p cubed. And 2 to the 1st power, 1 times 3 is 3, so we have 2 to the 3rd power. And then we saw negative exponents are the same thing as positive exponents when they flip. When the numerators goes, it goes to the denominator if it's already on top. Or if this was in the denominator, it could go up to the numerator. So that's a review of our exponent rules.